All right, so before we get to the washer method, let's take a quick minute here. We're going to do just part A of this for right now. And what we're going to do is we're going to find the volume of the solid generated by revolving y equals the square root of x, and from 0 to 4 around the x-axis. Okay, so this is just our basic disk method that we were looking at yesterday. All right, so what is our formula for the volume of something revolved around the x-axis? Tyler?
Pi times the integral of f of x squared.
Okay, pi times the integral of the function squared, and we're going to go, there's going to be some defined bounds from a to b here that we have to, that we're going to integrate over, okay? So, in this case, f of x is the square root of x, so, and our bounds are going to go from 0 to 4, okay? So our volume here is going to be pi times the integral from 0 to 4 of the square root of x squared, which of course is just x. So I know it's going to be pi times the integral of x. So that's going to be x squared over 2 integrated from 0 to 4. So if I plug in a 0, that's 0. If I plug in a 4, I have 16 over 2, so that's 8 pi minus 0 pi. So it's just 8 pi as our volume. Okay? Does that make sense? Right. So if we were to make a little bowl here, it kind of looked like this. You know, it would have a volume of 8 pi. Okay? All right, so let's talk about the washer method. And it sounds kind of complicated, but it's really not, okay? The term actually comes from the idea of, you have these hex, not octagon, hexagonal bolts in construction, okay? And, all right, so here's a bolt, and it's got these threads on it that you can screw something onto, all right? And then you have what's called a nut that has a hole on it, inside of it that's threaded, that'll screw onto it, and that's meant to hold things on. But what often happens is this head will get pulled through the material that you're trying to bind. So what they do to reinforce it is they make this nice circular thing like this, with a hole in it as well, that will slide over this and will kind of form this extra surface of reinforcement. But you can see the shape here is of the washer is just like a donut or something like that, okay? But the idea is that we have something going around the outside that has a certain radius, but then there's an inner radius that's cut out, okay? And that's what we're actually forming here when we're dealing with the washer method. We have two different radii. One is the radius of this inner circle that's getting cut out. The other is the radius of the entire object. Okay? Now, you guys are kind of familiar with this idea when you're dealing with areas or volumes or whatever. If there's a part that you don't want, what do you do to that?
Subtract it.
Yeah, you just subtract it, okay? So, as a result, if I were finding the volume of this entire thing without a hole cut into it, I would just use the volume formula that we looked at yesterday. It would be pi times the integral from a to b of that capital R of x squared dx. Okay? However, now I want to figure out how much I need to subtract. Okay, so how much do I need to subtract? Well, I'm going to do the same thing here. Pi times the integral from a to b of the inner radius squared dx. Okay? And you guys know, based on our distributive property and also the property of integrals, we could actually rewrite that so that our volume is going to be pi times the integral from a to b of capital R of x squared minus lowercase r of x squared dx. Okay? And by the way, notice one thing very important here. Notice you are squaring the functions before you subtract. Don't subtract them and then square the difference. Alright? There's a big difference there. Okay? So, we are going to square both functions and then subtract them. Alright, so we can see here our final function. Let's go ahead and see how this works. Alright, so for our first example here, we want the volume of the solid generated by revolving the region bounded by the graphs of the equations about the given lines. Okay, now notice here it says bounded by the graphs of the equations. When you see that written out, what are you automatically thinking? Between two curves.
Area between two curves. So integral of that.
How do you know what to integrate over? You gotta find the intersection points, okay? You gotta find the intersection points in order to define the region, okay? So, we're going to set these equal to each other to figure out where they intersect. We'll have x squared equals 4x minus x squared. We solve that. So we're going to have a 2x squared minus 4x equals 0. So 2x times x minus 2. So we're going to be going from x equals 0 to 2. Okay? Alright, so let's take a look at what we've got. Alright, so we have around the x-axis, we're going to have the integral. The volume is going to be the integral times pi from 0 to 2 of the outer radius minus the inner radius. So here again you need to figure out which one is on top, which is going to be the outer radius. Okay? Well, if you look at the graph of this, okay, we've got
Are you also taking the absolute value when you're doing the volume?
it automatically will end up being positive because we're spinning it around, so the squares end up making it positive.
No.
Okay, so here's our y equals x squared, and then we also have the x squared, or the 4x minus x squared. That's going to look like this. Okay, it's going to intersect over there. And right here, this point is at 2. Okay, so this region right here is what we're revolving around things. Okay?
So we're revolving only this region to get us some solid figure?
Yes.
So,
Yeah, so this one's going to look kind of weird.
so are you revolving like this or more like this?
We're revolving it around the x-axis,
Oh.
so kind of like it's, spinning around towards you or away from you like that. So the key thing is here, though, that you recognize that the 4x minus x squared is the one that's on top. So we're going to have 4x minus x squared. That's all squared. That's the outer radius. minus the inner radius. The inner radius is x squared, and we're going to square that as well. Okay? So you got some foiling to do, combine some like terms, and then integrate, and we can get our answers. So pi integral from 0 to 2, let's just do this kind of quickly here. We've got a 16x squared minus 8x cubed minus another 8x cubed is a minus 16x cubed, and that's a plus x to the fourth, but then I have a minus x to the fourth as well, okay, from the second half of that. So this is all I've got, okay? So that's dx, all right? I'm going to pull the 16 out right now to make my numbers smaller as I'm dealing with this. So I've got x squared minus x cubed dx. And now I'm going to go ahead and integrate. So 16 pi times...
How's the second number 16? 4 multiplied by x squared multiplied by 2 is 8.
Oh, wait, yeah. Sorry, I was doubling it too many times. 8, thank you. So I'll just pull out, not a 16, I'll just pull out an 8. And then this will be a 2x squared, so 2x cubed over 3. Thank you. And that's going to go from 0 to 4. Nice thing is, when you plug in 0, you get 0. So I just have to do that first part, evaluating it at 4. So I get 8 pi, and if I do 2 times 4 cubed is 64. So that's 128 over 3. 4 to the fourth divided by 4 is 4 cubed. So that's just going to be minus 64.
Is it 0 to 2?
0 to... Yeah, 2. Where'd I get the 4? Thank you. I'm keeping you guys on your toes this morning. That's a teacher line, you know, when they mess up.
So in this...
Alright, so 0 to 2. Alright, so we've got, hang on here, just 16 over 3, and that's going to be 16 over 4, so that's a minus 4. Alright, so that's 5 1/3 minus 4, which is 1 1/3. 1 1/3 times 8, 4/3 times 8 is going to be 32 thirds, and then I've got pi.
So why don't we change the pi to 3.14? All the pi is just erased.
Just leave it as pi because it's exact. If you change it to 3.14, now you're rounding and we lose precision. Plus, then you have to use your calculator. We don't have to mess with the calculator at this point. So let's talk about this second part, about the line x equals 6. Now be careful that you get the right line here. Don't do y equals 6. That one would actually be a little easier. Because we would then be able to, it would still be revolving the same direction. Here we're revolving it horizontally around a line x equals 6. So let me draw this real quickly. Okay, so you have this area. I'm just going to draw the area that we're dealing with from 0 to 2, and then here's 4, and here's x equals 6. Okay, so I want to revolve this around this line like this. You see that?
Yeah.
That's pretty wild. Okay.
There is a huge difference between 2 and a 6, like it's a 4, which means the region inside this hole is going to be huge.
Yeah, so yeah, there's going to be a lot more of a hole than there is going to be actual material going around this thing. Okay, so let's talk about how we would try to handle this. The first thing that we want to do is we would want to try to, since this is a horizontal one, we can try to revolve, or I'm sorry, express x as a function of y. Okay? Notice here, instead of going from 0 to 2, we're actually going to go from 0 to whatever that y coordinate is. Now, in this case, it happens to also be 2 because this intersection point was the point 2, 2. Alright? But understand here, when we integrate, we're going to be using y coordinates, not x coordinates. Okay? Because we're going to do horizontal. Now, the other thing that we need to do is we need to get this so it's revolving around the y-axis. And how would we do that?
You can just flip the whole graph and do another area of the same thing, but this vertical.
Okay, you're trying to reflect it and then do it around the x-axis. How would we do this around the y-axis here?
Get the equations so that they're in terms of y, and then integrate with respect to y.
Okay, we're going to integrate with respect to y, but how would I, instead of revolving around x equals 6, how would I get this whole problem to be revolving around x equals 0, the y-axis? What if we just shift the whole thing? Is that what you're going to say?
Yeah.
Oh, you got it. We're going to shift the whole thing over 6 units. So what do I do in my equations to shift everything over to the left 6 units?
-6.
Where?
It's +6 inside the parentheses, isn't it?
There we go. Add 6 to your x's. Alright? So if I made this y equals x plus 6 squared, and I made the other one y equals 4 times x plus 6 minus, we have minus x plus 6 squared. Okay? Now I've shifted that over 6 units. Now, as you can see, if I'm trying to switch x and y, okay, if I'm going to reflect everything across the line y equals x, that would kind of shift my whole graph around. So we got to get this in terms of y. So if I were to switch the x and the y,
Maybe a bunch of square roots.
or I'm sorry, I don't want to switch the x and y, I just want to solve it for x. Okay, so I'm going to have the square root of y equals x plus 6, so x is a -6 plus the square root of y. That one's not too bad.
Isn't it plus minus square root?
Because of our intersection, see how we only add half of the x squared, so we actually can just deal with the positive. Because that's all we need in this case. But yeah, there are cases where you may need the plus or minus. Now notice too, that's going to be the one on the inside. Alright? That's going to be the one on the inside radius. So as I'm setting up my integral, it's going to be the integral from 0 to 2 still. It's going to be something squared minus this -6 plus radical y squared dy. And don't forget the pi on the outside. So now I just got to figure out how to do the second part in terms solved for x.
And where's the second part?
The y equals 4 times x plus 6 minus x plus 6 quantity squared.
Oh, this one seems easier.
How so?
Oh, we don't. Oh, it's mine. Oh my god, I didn't. Maybe we solve it first.
just simplify it, you know?
Simplify it all out?
Combine like terms and then do that.
Okay, so let's do that. We've got y equals, we're gonna have a 4x plus 24 minus an x squared minus a 12x minus a 36. Okay, so that's gonna be a negative x squared minus 8x and a minus 12. Okay? So, let's go up here so we have some more room. So if I have y equals that, okay, well that means that,
We could get x equals using the quadratic formula probably.
No, you don't wanna find zero.
we don't want to find zeros, we want to get that solved in terms of y.
But I think quadratic formula allows for that, no?
Can't you do x squared plus 8x equals negative 12?
Right.
Then you factor out the x.
And then
Oh,
Oh, you're saying bring it over here, y plus 12,
oh,
and then factor out the negative,
oh,
negative x.
yeah,
and x squared plus 8x.
which equals to negative x multiplied by, or that, x. Then we'll factor out the x, and then we get x plus 8, which still does not work.
Yeah, it still does not work, so.
So
So what we need to do actually is we need to back up, and we can only use the quadratic formula if it equals 0, right?
yes.
So let's get it equal to 0.
So my
Negative x squared minus 8x minus 12 minus y. Now, let's do ourselves a favor here and divide everything by a negative 1. So that'll make us all positive. And what I'm going to do is I'm going to treat that 12 plus y as my c. Okay? So, x is negative b plus or minus the square root of b squared minus 4 times 1 times the 12 plus y. B squared minus 4ac all over 2a.
I think that's assuming that y is constant.
Well, no. It's just, I had to remember a, b, and c. A is the coefficient of x squared, b is the coefficient of x, and c is just whatever's added onto the end. Yeah. Yeah, 64 here.
so
Okay? So we've got x is equal to a negative 8 plus or minus the square root of, is 64 minus 48, so that's going to be 16 minus 4y all over 2. I can factor out a 4 in the radical, so square root of 4 is 2, so I have a negative 8 plus or minus 2 square root of 4 minus y
now you
all over 2.
yeah, now you factor it out, the 2, like you divide by 2.
Yeah, and that doesn't look too terrible, does it?
Well, that's why, yeah.
Okay?
Plus minus there.
Now we've got the plus or minus, but notice here, again, we're only going to need half of this because of the region that we're dealing with.
Okay.
Which means that we'll only need the plus 1.
We'll only need the plus 1, negative 4 plus the square root of 4 minus y.
But why not the
This makes it,
Yeah.
if you had the same thing, but with your area below the x-axis, for both equations for y, would you get the negative square root rather than the positive?
If I wanted,
The same thing but flipped on the x-axis and beneath it.
oh, I'd have to look at that, because this graph goes like this, this graph continues to go like this. Remember,
No, not
so the negative 4 minus would actually be like this right hand half of this, which I don't need. Okay?
Oh, so that's not,
Yeah.
so it's not.
Okay?
Yeah.
So here we have our integral. We need to FOIL some stuff, do a lot of simplifying, and then we can integrate. Okay? And then we'll have a result. So let's look at example 2 here. We want to find the volume of the solid generated by revolving the region bounded by the graphs of the equations about the line x equals 6. Now, again, this is a horizontal one. Alright, so we're going to have to also use what we looked at in our previous lesson about how to do things revolved horizontally. Okay, but let's first of all get an idea of what this is talking about. We have y equals 6 minus x. So here's the line that we're dealing with. Y equals 0, so there's the x-axis. Y equals 4, 1, 2, 3, 4. And x equals 0. So the area that we're dealing with here, guys, is this area right here. Okay? Now, here's where it gets a little bit interesting, alright? We don't want to revolve it around the x-axis. We don't want to revolve it around the y-axis. We want to revolve it around this line x equals 6. Let me do that with the pen. X equals 6. So, question here, what's the first thing that we ought to do? What did we see that we needed to do if we were revolving around something that's not an axis?
Like separate to different pattern, like for example a rectangle and a triangle.
Could translate.
Maybe. What'd you say, Terry?
Move them to the left and makes the x equals 6. Put x equals 6 on the x equals 0.
That's right. Okay, let's move everything to the left 6. So how do I translate things to the left 6 units?
You add it to the middle.
Add 6 to what?
X.
To x. Alright, so everywhere I see an x, I'm going to add 6 to it. So x plus 6 equals 6. That means x equals 0. There, now I'm going to revolve it around the y-axis like I want to. Okay? So here, I have y equals 6 minus, parentheses, x plus 6. Okay? Over here, I have an x plus 6 equals 0. Okay? And you'll notice now I'm dealing with x equals negative 6. And over here I have the line y equals a negative x plus 0. Okay? So once this whole thing has been shifted over, once the whole thing has been shifted over 1, 2, 3, 4, 5, 6 units, what you can see I'm actually doing now is I have the same area, however, now I'm going to be revolving it around the y-axis instead. Okay, does that make sense? Okay, so now here is my axis of revolution. Okay, now that's useful because now we're able to do the integration that we were talking about. Okay, we're going to integrate with respect to y. Give ourselves some space here. And in order to do this, I'm going to need y coordinates for my boundaries. So what are the boundaries going to be here? 0 and 4. Okay. 0 and 4, y coordinates. Alright. And then I need to do the one that's further away minus the one that's closer to, right? So the one that's further away is this x equals -6. So I'm going to have -6 squared minus the one that's closer to. Well, the closer one is a -x. And I'm going to square that. Okay? So you get the one further away from the axis minus the one closer to the axis. And notice what this is going to give me. It's going to look... The inside is going to look kind of like this when I'm all done. Okay? However, it's going to be a revolution, okay? Around vertically. Okay? So it's going to look like this. It's going to look kind of like this, just a cylinder with a cone cut out of the center. That's what that's going to look like as a three-dimensional object. Okay? So at this point all we have to do is finish the integral. I have... Oh wait, don't forget the pi. Don't ever want to forget the pi. Okay? Integral from 0 to 4 of 36 minus x squared. Now we have 36x minus x cubed over 3, evaluated from 0 to 4. Okay, when I plug in 4, I have pi times 36 times 4, this will be 144. Minus, I've got a 64 over 3. And then if I plug in 0, it's just 0. So this whole thing is minus 0. Okay. 64 over 3 is 21 1/3. So if I subtract that from 144, my volume is going to be 122 2/3 pi cubic units, whatever those happen to be. Mm-hmm.
The integral should be dy or dx? Or one should it be dy, one should it be dx? The dy and dx after the integral.
You have dy there. Why isn't it dy over dx?
Okay, the first step it says dy.
The next step is
Oh, wait. Hang on. Sorry. They're similar, so it wasn't making much of a difference there. Sorry, I do need to... Here, x is negative y. Okay? So I needed to... Sorry, this should be a minus y. That should be y. This should be y squared. This should be a y, and that should be a y. Thank you for catching that.
I have a question. So the inside is a point, it's not a cylinder. So how can you use like r1 squared minus r2 squared because it's a coin inside?
Well, because as y changes from 0 to 4, I'm evaluating whatever the radius is at that moment. So like at y equals 2, the radius of the outside is still -6, is still 6, but the inside is going to be 2. Okay? So yeah, that's how we're able to do that. Okay, thanks for catching my X's there. Okay, yeah. There's a lot to these integrals that makes it interesting. Alright, so for our last example, this one's a little bit easier because we are revolving it around the x-axis, so that's kind of nice. We have here, you're welcome, the line x equals 1. We have e to the negative x, so we've got this right here. Okay, that's e to the negative x. We have y equals 0 and x equals 0. So, guys, we're taking this right here and we're revolving it about the x-axis. So this actually, it's kind of nice. This one we don't even have to worry about the area between two curves, right? Because, if you will, the second curve is just y equals 0. Okay? So we're back to what we were doing the other day here. It's just the integral from 0 to 1. We're revolving it this way, so I'm doing it with respect to x, of e to the negative x squared. Okay? So this is pi times the integral from 0 to 1 of e to the negative 2x. And I just need to use some substitution. So I need a 2 dx and a negative 1/2 outside. Okay? And then the integral of e to the u is e to the u.
Is that negative half on the outside?
It's a negative 1/2. So I have a negative 1/2 pi times e to the negative 2x evaluated from 0 to 1. Okay? So we have negative 1/2 pi. E to the negative 2 times 1 is just e to the negative 2. E to the 0 is 1. Okay? And if you want to simplify that a little bit more, it's going to be a negative pi over 2e squared plus 1/2 pi. Okay? So, that's some washer method, disk method. We'll do some more with that next week. Alright? Have a good day, guys.